All right, we're going to talk about bond energy and bond length. In order to really understand bond energy, we have to know what potential energy is. So potential energy it's a form of energy that has kind of the potential to happen, I guess you could say. So if you take a ball and you hold it above the ground, it's going to have potential energy because as soon as you let go of it, it's going to move towards an area of lower energy, which would be down. Okay? Nature is lazy. It wants to be at the lowest energy that it has to be. That's why when you let go of a rock or a ball from a height, it's going to fall down because it goes from a high potential energy to a low potential energy. Bonds are the same way. So if we think of protons attracting electrons, not only is this proton attracting that electron according to Coulombs Law, but this proton is attracting that electron and that proton that electron. So when atoms are spread far apart, they have a high potential energy, but they end up sucking each other in, electrostatic attractions, opposites attracting, and so they move to an area of low potential energy. At this point, we have a covalent bond, where this nucleus is attracting this electron and that nucleus is attracting that electron, even though they come from opposite atoms. And there is a happy medium for the distance. If this proton was to suck in all of this electron all the way to where it's touching, well, that means that this nucleus is going to be almost touching that nucleus, and that can't happen. So we can try and push those guys closer together, but it wouldn't happen because at some point they're going to start repelling each other. And so there's this happy medium where the potential energy is the lowest it can be. If you push them together, you end up with high potential energy again. So it spreads out, evens out. So when you drop a ball, energy is released. Potential energy that you put in lifting it, it's released when it drops. Same thing when bonds form. Any time that a bond is formed, energy is released. That is the whole point of bonds. It is atoms being lazy in action. So they start out at high potential energy. When they bond, they go to low potential energy. That difference in energy has to go somewhere. It is lost. And by lost, given off. The same amount of energy must be added in order to break those bonds. So if it starts off with high potential energy and then goes down to low potential energy, when a bond forms, if you wanted to break that bond, you would have to give it back that same amount of energy that was released when it formed. It's just like a ball. If you drop a ball down to the ground and you need to put energy back into it to lift it up to the same height, you're going to put it in the same amount of energy that it released in falling. Let's say the same thing. Bond energy is the amount of energy that is required to break a bond between two specific atoms in a molecule, and it's also equal to the amount of energy that is released when the bonds form. So it's if you lift the ball or drop the ball, same amount of energy, just opposite directions. So for example, if you take hydrogen chloride and you break it apart into hydrogen and chlorine, so we've separated out those molecules, that's going to take 432 kilojoules of energy. If you do the same thing backwards, so instead you take hydrogen and put it with chlorine, all right, that's going to be going to high potential energy to low potential energy. That's going to release 432 kilojoules of energy. So these values are exactly the same, just opposite directions. One is required, one is released. In terms of energy, positive tells you that energy is required. That's a sign for an endo reaction, so you have to put in energy. A negative, that means exo, that means energy is released. So anytime you see positive and delta H, which is the sign for energy, positive means that you're having to put that energy in, negative means you're getting that energy back out. When elements hook up, when they get together, truth is they're only looking for one thing: lower potential energy. So if we have two hydrogen atoms that are separate, the only reason they'll bond is if there's something in there for them. If they're going to get out, a little bit of lower potential energy. So here they are. This is a scale that shows us energy. So right now the energy is at 0. When those two hydrogens right there come closer together, you can see that they're starting to lose some of their potential energy as they move closer, because the nucleus is attracting these electrons and that nucleus is attracting these electrons. And as they get closer and closer, eventually they hit this low point, and that is the point where the hydrogen-hydrogen bond forms. Now, if we were to take those two and see how they're slowly getting closer and closer together, and we were to push them really close together, you're going to end up having that repulsion between those nuclei, and it requires more energy, and so it'd fall back down to that length. So what this is, the internuclear distance, that's the distance between the nucleus, is graphed down there, versus the energy. So right now, negative 458 kilojoules of energy. That means this bond right here, those two coming together, releases 458 kilojoules of energy. But if I went from here to here, so if I took those and separated them, I would have to put in 458 kilojoules of energy to get up to that point. And then down here we see the distance. So when they're spread out like that, almost at 0 kilojoules, but as we move over this way and they get closer, but then eventually they get too close. Alright, here's our old friend Coulombs Law, just worded another way. So as the atomic radii of bonding atoms increases, that means that the bond length will increase and the bond energy decreases. So all that we're saying right there then is as we increase that distance between atoms, here's the nucleus in the middle, there's the shared electrons. Look at the distance between that proton and that shared electron, that proton and that shared electron. It's not very far, so according to Coulomb's law, if you decrease the distance, you're going to increase the force. That means that this bond would be fairly strong. However, right here, the radius is getting larger, which means the distance between the nucleus and the shared electrons is getting much larger. If you increase the distance, according to Coulomb's law, force will go down, and that means we would have weaker bonds. So this bond would be harder to break than this bond. It also means that less energy is released when this bond forms versus this bond. Since that one's more stable due to a stronger force, it's going to release more energy when it forms, and it's going to require more energy to break. Okay, here's 3 examples. These are all carbon bonded to different halides. And if you look on your periodic table, chlorine or chloride is the smallest, iodide is the biggest. So these go down on the periodic table. All of them are single bonds, and we can see the bond energy to form this guy right here, which has the smallest bond length because chloride is the smallest, is 339 kilojoules per mole. That means it would release 339 kilojoules. If it were to form, it would require 339 kilojoules to break. Then we move on to bromide, which is a little bit bigger than chloride. Okay, now the bond length has gotten bigger, so that means the bond energy has gone down. Coulomb's law. Iodide, the biggest, its bond energy is the lowest. Coulomb's law again. And so let's just note again that as the atomic radii increases, bond length will also increase. And if bond length increases, potential energy increases and bond energy decreases. Okay, these are called space-filling models. Just represents the atomic radii. You can see that each different element is represented by kind of an orb. They're pushed together, and that just represents shared electrons in the middle. So which molecule has the least amount of potential energy associated with its bonds? And then also, which bond has the lowest bond energy? Alright, so if we take a look at these real quick, this one has the shortest bond length, this one has the longest bond length. So shortest bond length, that means that we'll have the lowest potential energy, because potential energy increases with bond length. And this other one would have the lowest bond energy, because bond energy decreases with bond length. Alright, single bonds, double bonds, and triple bonds all have different bond lengths, and we can think of it just in terms of electron density and attraction. So with a single bond, you have 2 electrons in the middle. Here's your nuclei right there. Not a lot of negative going on, so not a ton of attraction between those two, just enough to hold them there. Double bond, whoo, look at that. We've doubled the electron density in the middle. That means that these protons are going to be a little bit more attracted to what's going on down there. And then with a triple bond, oh man, 6 electrons in one place. Those protons are all over that. They're going to move in, and we're going to wind up with a short bond length. So as the number of bonds increases, the bond length will decrease because those protons are going to be attracted towards that electron density. Let's think about this in terms of what we just talked about. If bond length decreases, what's going to happen to the bond energy here? So as we go from a single bond to a triple bond, how will bond energy change? We can answer that very question right here. So as we go from a single to a double to a triple bond on these 3 diatoms right there, we see that the bond length decreases just like we saw in the last slide. If bond length decreases, What do you know? Bond energy increases. Coulombs Law right there. We're decreasing the distance. We're going to increase the energy because of the increase in force. Alright, bond order. This is a term that you're going to need to know. So a bond order is just a fancy way of saying the number of bonds. So the bond order is the number of bonds between two particular atoms. So if you have a single bond, what do you know? The bond order is 1. If you have a triple bond, hey, it's 3. So when bond order increases, a couple things happen. The bond length decreases. Electron density in the middle kind of sucks everything together. The potential energy associated with that bond will decrease. So as bond length goes down, so does potential energy. And as they move closer together, that's Coulomb's law, the distance is decreasing, so force is increasing, bond energy increases. So here's some ball and stick models. These would just be ones that were built. So which carbon-to-carbon bond in which molecule has the lowest potential energy? And which carbon-to-carbon bond in which molecule has the lowest bond energy? So remember, potential energy and bond length kind of go hand in hand. So the lowest potential energy would be the one with the lowest bond length. That would be, even though these look like they're the same distance apart, this guy right here, it's got a triple bond, so it'll have the shortest bond length. Therefore, it would have the lowest potential energy. This guy with its double bond, it's going to have the larger bond length, which means it's going to have the lowest bond energy.